Okay. So glad to see people are here. Hopefully things are going well. Getting near the end of the week, into week 9. A few reminders, the reading assignments, remember, due tomorrow at 5 o'clock. I'll probably send an announcement again about this tomorrow, I think, through Blackboard. Maybe that would be helpful, but just as a reminder, when you're completing the reading assignment, the main goal of the reading assignment is to develop some questions about the material in chapter 16. So there aren't really any questions to answer that are in the reading assignment that you would necessarily write any answer down to. But the goal would be to develop some questions that you might have about the material in chapter 16. Maybe come up with 3 or 4 questions that you feel are important, that you feel like you need to know, about. And so just submit those. I think you can probably submit the questions directly on Blackboard, or if you prefer, you can simply type them into a blank Word document and submit that as well. Try to keep the questions maxed out at about 4 or 5. I want to be able to respond to the questions as I see them come up. But if you start asking, if everyone asks like 10 questions, it might be too many. So try to keep them, down to maybe 3, maybe 4, maybe 5 questions or something like this. Homework 8 on my stat lab is due on Monday at 5 p.m. So that's sort of standard. It's kind of what we've been doing so far with the course. And the written assignment 6 is due on Tuesday. Written assignment 6 concerns confidence interval construction, which we'll talk a little bit more about today, including doing a few examples on Statcrunch to kind of see what that assignment might be getting at. Another sort of generic announcement, next week, exam 2 will take place. I'm going to make exam 2 available on Monday morning at 8 a.m. The exam period will end at 11:59 p.m. on Friday, just like exam 1. I don't think that the parameters of the exam really need to change. It seems like, from a purely technical point of view, exam 1 went fine. I don't think people had a lot of technical obstructions in completing the exam, so keeping the format the same seems reasonable. If you have any questions about that or any concerns, just let me know. The material on the second exam will consist of chapters 10 through 15 and sections 16.1 and 16.2 from chapter 16. And that's enough for the second exam, I believe. So we'll sort of cut it, I think, right before we get into any serious talk of. So it sort of ends with discussion of the sampling distribution. That's maybe a good place to stop on the exam. I imagine, given what's in there, it's probably not more than about 10, 15 questions, much like exam 1. The type of preparation you would do, I would kind of advise a similar approach to sort of how you prepared for the first exam. Go back, look at some of the reading assignments that you did. The reading, I think you probably don't want to go back and completely reread everything because that would take too much time. Go back and review some of the My Stat Lab homework assignments that you have done. You might want to do this mainly because the question pool from which the questions on exam 2 are drawn is similar to the types of questions that you might appear on the homework. So, they obviously will not be exactly the same. There won't be reproductions of individual questions on the homework on the second exam, but at least you have some idea of the type of questions which might be reasonable. Any questions so far about any of this? Yes, Grace.
So when we submit reading assignment 16, do you want us to submit like notes we take and questions, or just the questions?
I think the questions are sufficient.
Okay.
I don't necessarily need to read through your own notes on it. I mean, the reading assignments, I think, are summaries of what's in those chapters anyway. So, but try to keep the questions maybe down to 5 or fewer. Otherwise, it's going to take too long for me to be able to respond to them all, I guess. So if you have more than that, we can always go offline, if you will, and have discussions about those questions.
So do you want us to submit like 5 for each part, like parts 1 and 2?
Yeah, sure. You can do that. Yeah, you don't have to limit yourself to 5 questions from both. If you have questions, you should ask the ones that you think are the most important. And if you find yourself having additional questions, we can always talk about those. So you can always send me an email, or we can talk during office hours or something.
Okay, thank you.
Lily, yes.
So when we're writing these questions, should we write them at the bottom of the document, or just kind of at the top, or separately? And then B, are these like discussion questions that we genuinely have to ask you? Are they supposed to be like problem type questions for the classmates? Like, what kind of questions are you looking for?
Right. So I'm mostly looking for questions that you might have about the reading. So for example, you read something in the book and you're not quite sure why something is there. You would ask about it. An example, I mean, there are probably many examples of this which might show up in this particular chapter, but they don't necessarily have to be, they can be, I mean, you have the freedom to kind of ask whatever you want. I mean, if you read I guess the issue is if you read chapter 16 and you find you have no questions at all, and the exposition is just totally clear, then, maybe there's not a whole lot to ask. But in that case, you might want to ask for particular examples, or you might say, look, how do you do this? So you have a particular problem and you try to, you ask, so you could ask a question about a problem. Maybe that's sort of what one of the things you're talking about. But I guess what I have in mind is if you have any questions about what's in there conceptually, you read it, you don't understand something, just write that down. Does that make sense?
Sort of. So there has to be 5 questions exactly, and then
no, there doesn't have to be.
So that's not like part of the reading assignment that we're graded on, is the questions?
No, it's not. I'm not grading on, and I'm also not grading on the number or the quality of the question.
Okay.
Right? Like it can be anything you want. All I'm saying with 5 is that I think that if everyone starts asking more than 5 questions on both of those, I mean, from a practical point of view, it's probably going to take me too long to answer them all on Blackboard. So I hesitate to say you can ask anything you want, because it would wind up with me never finishing the grading. And so try to keep the questions below 5 questions if you can, like lower than 5.
Okay.
If you ask, like,
Okay.
if you read it and you think, look, I totally understand what's going on here, that presents a different issue. I mean, it's a good thing to be able to read what's going on in there and understand what's going on with no questions. But if you're in that position, just be creative with what you ask. If you want to see a problem done using some of the techniques, you feel like the exposition is insufficient in one way or another, you want to have or take some additional look at something that the author says or it's in the summary, that's a fine question too. It can be beyond the scope of the course, if that makes sense.
Yeah.
So it doesn't have to just be purely proceduralistic or even about the I guess I would say even limited to what even limited to exactly what you might be reading. So one question that might come up is the author, and it should come up. I mean, it's a good question, but the author makes a big deal about, I think this is in section 16.3 and 16.4 of the text. The author makes a big deal about what you can say and not say about a confidence interval. And this is always a natural question that students have, because when the author is describing the sort of statements you can make about confidence intervals, it seems like a bit of a dodge, because the author's writing something like, well, you can say that you're 95% confident the parameters contained within this interval. And there's supposed to be some meaning behind that. Like if you tell someone this, I'm 95% confident that this interval contains the true value of the proportion, then it's easy to, I mean, an example, it's easy to confuse that with the statement, the parameter has a 95% chance of falling within this interval. And the author is saying that you're not saying that, but you are saying this weird thing about confidence. And most students find this discussion about confidence versus probability really weird. And the first time you see it, and I guess it is weird. And so it's sort of a natural place where you might actually ask some questions about, conceptually, what is it that we're actually doing with the confidence interval, which would cause us to take the trouble to distinguish between these two different things we're saying. Who cares, right? Like, why would you care enough about this? What does it mean that we're actually, I mean, so that's the kind of thing, if that makes sense. You could ask that. If you can formulate a question around those sections, I think I'd be happy if people did that. And then there are certainly some other things in there, which you also might ask of that nature. Does that make sense?
Yeah. And then another question is like, so in those reading assignments, for the first one, there was like maybe a piece or two that we were supposed to write in, but like how are we being graded on this if there's very little that we have to write in these reading assignments?
I'm simply giving you a grade for turning it in.
Gotcha.
So it's like if you turn it, I think they're both worth 5 points apiece. So basically, if you turn in anything and if it's not nothing, right? Like if you don't just return the document and it's blank with no accompanying questions, like it doesn't look like you've read it, then you would get very little out of the 5. But if it looks like you've engaged with what's in there with the material in chapter 16, I'll give you 5 points. That's how it's going to be graded. I just want to see the questions, I guess. Is that okay?
Yep. Thanks.
Other questions about this? Yeah, and so when you're thinking about it, even if you understand everything that's in chapter 16, work a little bit at some of the ideas that are sort of on the fringe. Try to make yourself think of something that you might ask that you might be interested in. I mean, again, like I guess I gave an example. We'll talk a little bit more about this today, where the authors seems to be going to a lot of trouble to distinguish between statements like we're 95% confident that the interval contains the parameter, and statements like the parameter has a 95% probability of being within this interval. An author wants to draw a distinction between these. And you should really ask about that. That's important. And it's a fundamental question about, I mean, you don't have to ask about it, but it's a nice question to ask if you're interested in this kind of thing, because it's sort of a fundamental distinction between the approaches that we use in a course like this, where the framework is very classical, and there's one particular assumption we're making when we're thinking about these problems of estimation, and other frameworks which can be used to analyze similar problems. And there are some things to say about that. And I'll say a little about that today, but it may not be completely enlightening, but it's worth sort of dwelling on and thinking about more than just like a day. And you don't. I can't totally enlighten you about that. It would be something that I would say, like, distinguish, and this is why the author wants to talk about it, but you have to kind of, live with the issue for a while to kind of work out why the author's trying to do that. So good. I guess if there are no more questions, which are of kind of a procedural nature about the grading, about the work you're supposed to turn in, about what's expected, then I'll move on to the material that we'll talk about today, which concerns confidence interval construction for proportions. Now, regrettably, I guess I have to say a little bit about how this stuff is done. I always feel like I have to describe what's being done, give you a couple of formulas that you can use, maybe show some examples of what the idea might mean, and then I'll let people work on some problems. But it will be a day where I feel like I have to write some things down, talk about some things. But then it will wind up being the case that, the actual act of constructing a confidence interval is rather easy. But how you get to the point where you think that this type of interval is doing what you want it to do is maybe a little trickier. So let me get started. I'll break people into groups in just a little bit, but maybe not yet. So, last time you might remember we were about right here. We were talking a little bit about our goals. The goals for the section are to step up the estimation process a bit from where we're currently at. So if you're thinking about this chapter as one in which we are talking about how a sample proportion like P hat might be used to say something about an unknown true proportion P, all we have at this point are point estimates coming from a random sample, and maybe a way of gathering up and discussing the characteristics of, if you will, all possible point estimates P hat that could come from all possible random samples. And that's kind of where we're at. So I haven't really talked about the conditions very much about, when the sampling distribution for P hat looks normal. I feel like I should say something about that, but I'll probably just sort of allude to it in just a bit. So the last point here, it's natural to think that, we're going to be able to make some probabilistic statement about a parameter location. That's usually what people want to do when they want to read this chapter, but regrettably the methods, I guess, regrettably, maybe regrettably, we won't take this line. So if you want to make a statement about the location of the parameter in some probabilistic sense, within a fixed interval that you somehow make. Unfortunately, the methods of Stat 202 won't get you there. So what I mean by that is we won't be able to, ultimately we won't be able to say things like the true proportion has a, X% chance of falling. Just to take an example in the interval. If you have a fixed interval, let's just say we're talking about the interval 3 to 4. We'll really never be able to say anything like that in this class. And the reason, the author talks a little about this, but I think it is a little unclear, but you have to live with it. The reason for this is that in this class, the methods we're discussing assume, it's an axiom in some sense of our approach, that a parameter P, the thing we're trying to estimate, is a fixed but unknown number. So the consequence of that turns out to be a lot more profound than you would guess. So to be able to make a statement like the one that you see in quotes here, you would really need P to come equipped with a probability distribution. You would need P to act like that one question that you were dealing with on written assignment 5, where you're dealing with ACT scores which came with a normal distribution. And so if you're dealing with ACT scores which come with, say, some known probability distribution, then it's possible to discuss the probability that the random variable which keeps track of those scores falls within a certain range. There's a probability distribution to discuss. But if you think about the basic thing we're assuming when we're doing our inference, when we're doing our estimation, we're not saying that P is that way at all. We're saying it's a number. So there's no probability distribution to discuss. The variability, the randomness, is associated to the intervals we'll construct rather than the parameter. And that's a very confusing point. If you have questions about that, you should definitely ask on the reading assignment, because I think that's really confusing about this type of approach. The way of constructing a confidence interval that we're going to talk about does not give the intuitive answer. Instead, what we're going to wind up doing is we're going to wind up, I'll talk about the technical details in just a second, but roughly speaking, we're going to pick up on a random interval coming from a larger family of intervals, which are constructed using some sort of consistent process, a consistent mechanism. And so what we're going to wind up with our interval is a plausible range of values for the parameter. Do you know for sure that the parameter will be in the interval? The answer is always no. The parameter may or may not be in the interval, but the randomness is associated with the interval rather than the parameter. So to write down a little bit about this, we will construct an infinite family of intervals, some of which contain P and some of which don't. The confidence level that you might read about in chapter 16 is a description of the proportion of intervals under certain conditions in this family which contain the parameter. And the act of obtaining or getting, I guess, a random sample from the population of a certain fixed size, of a certain fixed size from the population, is equivalent, it amounts to randomly selecting one of these intervals. So practically what, there's a formula. We'll talk about that in just a second. We'll maybe talk about the, theoretical development. But what I'd like to do right now is just to kind of show you a little bit about, what that might mean using Statcrunch. So if you go to Statcrunch, there are a lot of nice features. And one of the nice features that it has is that you can kind of simulate this idea of a confidence interval, and, the confidence level is something that you can actually discuss. You can see what's going on. If you go to applets, confidence intervals for a proportion, what I'm going to do in this case, and it's cheating a little bit, but in this example, what I can do is I can select the true value of the proportion using entering some number in here. So for the sake of simplicity, I think I'm just going to leave that at 0.5. When I have a confidence level of 95%, I'm going to leave that as 0.95. The sample size is 30. So what will happen? What we're about to do, what you were about to see, is a simulation of drawing or constructing a certain number of confidence intervals from within the family. What I'm hoping that you're going to see, because the sample size is large enough, is that the number of intervals which actually contain the parameter is about 95% of the number of intervals that we'll wind up creating. So when you hit compute, don't worry about this so much, but when you hit compute, you'll see something like this. So in this particular image, what you're going to see is 100 different intervals. So these are listed from 1 to 100. They're represented in this image in front of you as these bars. The true proportion you see corresponds to the black line that you see running down the middle of the diagram. When an interval contains the parameter, that means that there's an overlap between the horizontal green line that represents is a visualization of the interval itself and the line. When you see that something red like this guy right here, what you have on your hands is an interval that does not cover the parameter. So using the methods that we're talking about, Statcrunch can kind of build these sort of automatically, and it built 100 of them. It's a 95% family, and so what you're seeing is that 95 of the intervals contain the true parameter and 5 don't. Most of the intervals contain the parameter, and so the act of getting a random sample in a case like this might be equivalent to picking one of these intervals out at random. And it will either contain the parameter, it will either cover 0.5, or it won't cover 0.5. One of those two things is true. But if it's a 95% confidence interval, you feel comfortable, I think, presenting to people that interval as an estimate for the parameter. Do you know that the parameter is really contained in the interval that you are presenting to them? No, maybe it is, maybe it isn't. Maybe by bad luck, if you will, or by sampling variability, more technically, you might get an interval that looks like the red one. You present it to someone, you say this is a 95% confidence interval for P. Now it turns out P in this case is not in the interval at all, but it's still a respectable thing to do. A reasonable person would believe that the confidence interval that you present at that confidence level, if everything else is done in the right kind of way, would contain the parameter. They would respect the interval that you present them as being, a reasonable approximation for the actual value of the parameter. Reasonable people would believe that the parameter is contained in the interval. So before I move on, does anyone have any questions about what I'm trying to say so far? The methods that we will use amount to producing an infinite family of intervals at a particular level of confidence. That confidence level represents the proportion of intervals within the family that actually contain the parameter. So if it's a 95% family, what you're saying is that you think that with the methods that we're talking about, which I admit are unclear right now, you're thinking that 95% of the intervals within the family contain the interval, 5% don't. And the act of getting a random sample and effectively computing a value for P hat amounts to selecting one of these random intervals at random and then looking at it. So you might get one that contains the parameter, or you might not. But if you're in a 95% family, you feel good about your choice. Either it does or it does not contain the parameter, but it's respectable. It's sort of intellectually respectable to tell someone something like that. And it's respectable to believe that the interval represents sort of a range of values that are reasonable, that are plausible for the parameter itself. Is it in fact the case that the parameter is contained in such an interval? The answer is no. Maybe it isn't. Maybe it is. So does anyone have any questions about this so far? This is the hardest point about this. Statcrunch will actually compute these for you. We'll have a technical discussion in just a minute, but before we have that discussion, does anyone have any questions? Anything at all? So it's okay. All right. So what I will continue to talk about maybe for a bit is how you might actually build these and what you're going to find, and I'll show you kind of why this discussion will be made obsolete very quickly. But I feel like I have to have it anyway. When you go to Statcrunch, there's a way to get at confidence intervals. And so, how do you actually build a confidence interval for a what am I trying to say? For an estimate. If you go to things like proportion stats in our case, and you look at one sample, you can provide Statcrunch with a summary, and you can sort of automatically build a confidence interval. So I'll do that real quick. Suppose that you're trying to, like in our problem with the so here's an example with the coin problem we were dealing with. Suppose we wanted a range of values for the probability of getting heads at a level of 95% confidence. I could report that the number of successes out of 50 flips is 30, like the number of heads is 30, number of observations is 50. And when I hit compute at the 95% confidence level, what will happen is the Statcrunch will compute for me the lower and the upper confidence limit associated to what I enter. So what this is saying is that, okay, look, we flip a fair coin, or we flip a coin, and we don't know if it's fair or not, 50 times, we wind up getting 30 heads out of 50 flips. We compute a confidence interval based on this. And the lower limit for that confidence interval is about 0.464. The upper limit is about 0.73. So for that coin could generate many different possible outcomes. But one of the random intervals that you would select, given this outcome, 30 heads out of 50 flips, looks like this. So for a lot of the problems that you're going to wind up doing from a practical point of view, you can black box them in a sense. Statcrunch will compute confidence intervals without too much work. So in some sense, it's nice to know a little bit about the formulas and kind of what's going on. The author presents them, and we'll use them a little bit today. But the truth of the matter is you can get Statcrunch to do this. You can play around with this confidence interval calculator. You can edit. So I'll do that right now. What if you had a higher level of confidence? You're going to find that the interval is a bit wider. I don't know if that's surprising or not. The lower limit and the upper limit are reported. So the discussion we're about to have, you probably will use Statcrunch to compute confidence intervals quite a lot. But there probably needs to be some discussion about kind of what their genesis is, where they come from, and I think that's probably what I want to do right now. To be more precise about this interval or family of intervals construction, to be precise, we want a formula for our intervals to look like this. So it will look like, it will have the value of the sample proportion right in the middle, but it will look like P minus some error and then P hat plus some error. And when you write this down, you can kind of see why you might get an infinite number of intervals. Yes, Lily?
Wait, so you said P minus error, but then wrote P hat minus error?
I meant P hat, yeah.
Okay, all right, got it. Thank you. Just making sure.
Yeah, P should never be in any of this, and it has to do with this discussion about P. So P, so I misspoke. It's P hat minus the error and P hat plus the error, right? P hat's right in the middle. And so you're dealing with the family of random intervals. The variability always occurs within the interval and never with P. So P, the thing you're trying to estimate, may or may not be in the interval, but you shouldn't mistake it for P hat. P hat is the estimator for P, and the intervals that you're talking about form a family of interval estimates for P, some of which do a pretty good job of estimating P, some of which don't contain P at all. And the error, it sort of represents a distance or a length that you're sort of expanding around P hat in order to get a little bit more precision in the estimate. You're describing a range of numbers for P rather than P, just one. And so the error is somehow connected to the level of confidence for the family. And so the author provides a description of how that connection is made. I'd like to talk a little bit about it as well. Just a reminder, how do you come up with it? How is it connected to the confidence level? In what way? So let me move on. I think I need the nice blank page. Remember that the basic tool that we have is the sampling distribution of P hat. So the analysis that we're going to do to come up with the error term, we're assuming that P hat has a normal distribution. The center is P. P hat has characteristics where the center is P, the mean is P, the expected value of P hat is P. And the standard deviation is P times 1 minus P divided by N. There's always some sort of fixed sample size lurking in the background. So I'm going to draw a picture here. I'm going to move 1 unit of error to the right and 1 unit of error to the left here in this diagram. And if you think about it for a minute, in our formula, just to remind you, our formula for the interval is not P plus or minus error, it's P hat minus error and P hat plus error. But the error that you're talking about, they represent the same sort of numerical distance in here as they do here. If you think about it for a minute, you'll realize the following fact. If P hat is in the interval, and this time I'm going to write this deliberately. If P hat is in the interval P minus error P plus, it's not a random interval at all, it's just one interval. So then the interval P hat minus error P hat plus error contains P. So why would I write something like this? Like how do you make sense of it? So if you take a look at this interval of numbers, what you're describing is a range of numbers on this horizontal axis, which extends from this point right here over here. So all this statement means is if you find yourself with a P hat right here that's within that range, that interval will cover P because the gap between P hat on the left side, P hat minus the error will sort of be enough to extend, and it will extend over here. Won't quite get over here, right? Because P hat's to the right of P in this case. But what we're saying is if you have something that looks like this, it will cover P because the error, the P is too close to, P hat is too close to P from the perspective of this diagram. So it would be like saying, okay, like if P hat's right here, then an interval which looks like this, would be from here, maybe to about here. You definitely have P in there. Yes, Lily?
So in the interval P minus error, P plus the error.
This one right here?
Does P hat have to be in that interval?
No. No.
Okay, so then why, if you have the P hat minus error,
yeah,
that is above P, and then the P hat plus error is still above the P, then how does it contain P?
It doesn't. It doesn't. It doesn't.
Then why? What does that mean?
So that you're exactly right. It doesn't. So if P hat, so and that's exactly the point. That's exactly why the family of confidence intervals, every confidence interval in that family does not have to contain P. So what all the statement is saying is if P hat is within that interval, then the interval, then our sort of generic formula does contain P. And that's, I guess, just because geometrically, if P is here and that error are the same, then we can cover P with the interval because the error sort of extends to contain P, and that's true also on the left. But you're right to point this out, because if we have the same diagram, here's P, it's over P. We can also say this: if P hat is not in the interval P minus error, P plus error, then our interval P hat minus error, P hat plus error, does not contain P. So this statement amounts to the observation that if P hat finds, so that sort of represents P hat stood over here. If you take a random sample and you wind up being outside that interval of numbers, if you're over here, then the right-hand error is not enough to get to P. You're beyond this measurement here. So P hat is over here. The error term, the right-hand endpoint, P hat plus the error term, would not go far enough to the right to contain P. I don't know if that answers your question, Lily, but you're right.
It does. Get it.
Your interval doesn't have to contain P. And because of this fact, if we wanted 95% of our intervals to contain P, I think I need to go to the next page, then what would the error have to be? If you're dealing with a normal distribution, I always draw these very, very poorly. Sorry about that. So it's P plus error, P minus error over here. This is normally distributed, so P hat is normally distributed with these characteristics. I'll write the standard deviation, as I normally do this way right here. To get that interval, what we're asking, essentially we're changing the question a bit, and we're asking, look, what does the error have to be so that 95% of the P hats fall within this range? If you think about this for a minute, you realize that the error must be, in this case, if we want this 95% family, this error must be about 2 times, so 2 times the standard deviation of P hat, which is 2 times, that thing right there. So it's this thing P times 1 minus P divided by N. Maybe it's better to think of it that way. That's sort of a breakdown. Now, why is that? That's just the empirical rule. So the process is that we take this question and we notice that if we're just dealing with the normal distribution and we're trying to get a handle on how the error can be manipulated in such a way so that 95% of our intervals, which have this appearance right here, contain the parameter, this is equivalent to trying to answer the question, what would it be? What has to be true about the error term so that 95% of the P hats fall within an error's distance of P? And so if you're trying to answer that question, you realize very quickly, if you're dealing with the normal distribution, then P hat, in order for an interval like this to cover P, to contain P, P hat's got to fall within a couple of standard deviations of P. And so that's kind of where this formula comes from. Now, 2 is not quite right. It's actually 1.96. It's not such a big distinction, but that's the basic idea. Other confidence levels you can control. So basically, we can control, or we can calibrate the error to the confidence level by figuring out how many standard deviations we need to be, well, how many standard deviations we need in order to assure ourselves that a confidence level's worth of p hats fall within the interval p minus, so I think it's usually called z star, sigma p hat, p plus, and that's not p hat here, that's p. So I don't know if that type of formalism makes sense, but again, just to reiterate, all we're really saying is that p hat's distribution is normal, so a discussion of the confidence level is the same as the discussion of standard deviations away from p. Yes, Lily?
Can you pull that up again? I wasn't done writing it down.
Yeah, sorry.
Thank you. All good, all good, all good.
Yeah, and so, that formalism, and so you're just trying to think about, well, look, if I have a 95% confidence interval, I can assure myself that the family of intervals that I come up with using the formula, 95% of the elements of the family will cover p, provided that the error term looks like 2 standard deviations away from p. If you're dealing with a 90% confidence interval, then you're talking about maybe something on the order of about 1.65 standard deviations. So the formula varies with the confidence level. If you're talking about a 99% confidence interval, or a family of those, it's a different value of C star. But in effect, it's the value of C star that's actually controlling for, that is associated or corresponds to the confidence level. So, I'll write a few of these down, just for the sake of completeness. A 95% confidence level tends to be associated with a value of Z star that looks like 1.96. I think we're using 2, it's about the same. 90%, somewhat less, 90% confidence level from memory, I think that's about 1.65. I don't actually remember offhand, somewhat embarrassingly, what a 99% confidence level is. So it's 1.96 sigma, sigma of p hat, I guess I should say, 1.65 sigma p hat. This is some number. Let me compute it real quick using Statcrunch. In order to figure out what the Z star should be, just go to Stat, Calculator, go to Normal, and you might as well just use the standard normal distribution to work this out. Go in between. You're trying to arrange sort of a symmetric interval around 0 to figure out what the value for Z is. To get a 99% confidence interval, you set this area to 0.99 and you get the cutoffs. Looks like it looks like you need to be about 2.56, or rather 2.58 standard deviations away, if that makes sense. 95%, about 1.96. 90%, there's our 1.65 or thereabouts. So, again, the red area you're talking about is where we kind of, in some sense, want the p hats to be located within. So let me go back, just sort of to be complete. It's about 2.57 sigma p hat. One more note, and this is sort of should add a little suspicion in your mind about the method. If we don't know p, and we don't, right? What do we do? What do we do about sigma of p hat, the standard deviation of p hat? The only thing we can do is estimate it. And so in general, for the type of formula-like construction, if we don't actually know what p hat is, we would use the formula p hat 1 minus p hat divided by n, take the square root of that. And the author refers to this as the standard error of p hat. There's always a difference in language depending on the textbooks that happen to be used in the course. And so when you're talking about the standard error, the author is very careful to make a distinction between the standard error which is an estimate of the standard deviation. And one more note maybe about this: if n times p hat is greater than 10 and n times 1 minus p hat is greater than 10, then this estimate, their methods are pretty good. And that basically has to do with the fact that if this condition is more or less satisfied, we actually expect the sampling distribution for p hat to look a certain way. So in most practical examples, when you're actually trying to use a formula to come up with a confidence interval, these conditions are certainly satisfied. So let me see how much time I've burned up. So you have a little time left to work on some things. Before I move on, does anyone have any questions about what we're doing? I mean, again, another thing to say about this is, this treatment, this discussion, I think it's important if when you're trying to think about how you come up with a confidence interval and the meaning of it, it's important to internalize that discussion and think a little bit about how you're going to come up with them, or what the theoretical background is, if you want to go on and think about this stuff in other contexts. So, if your goal is ultimately to take a subsequent course and you need to know, conceptually, like, look, how do you actually do this? Like, where does it come from? What is a confidence interval? It is important to internalize, I think, the conceptual discussion about how you come up with one. And this discussion is in some form, I think, in the textbook as well. But Statcrunch will compute these. And so that's also worth remembering, that you can get the confidence interval by just asking Statcrunch what it is, and you can get it. It's completely black boxed. And so in a way, I think maybe the interpretation of the interval might be important, at least for this class, and maybe for some others. But if you want to get into a deeper technical discussion, trying to understand how you come up with one and what one is probably important. As is probably a more thorough discussion of the conditions than we really allowed ourselves this week. So any questions about this so far? Is it good? Yes or no? Now, what I'd like to do is I'd like to have people break into groups. I'm going to share the screen again. The handout where we're going to work on, I think, has confidence intervals in the name somewhere. What I'd like people to do, what I'd like the groups to do, is to think a little about question 1. Don't worry about 2A right now. We may return to that later. Worry about 2B and 2C. When you're thinking about conditions, you're mostly interested in whether or not, you can't really say too much about a few of them, but if you really want to think about what A is asking, the only condition that you can actually check is whether or not NP and NP hat and 1 minus, whether or not this condition is satisfied. And it's an important condition, so you can check it. The others, when you're trying to convince yourself, whether or not the sample is too large, usually the methods work pretty well if the sample is less than 10% of the population. And of course, that's going to be true in this example. The independence condition, which the author mentions, is always totally unverifiable unless you have access to the actual work that people did. So when you break into groups, what I'd like people to do is to compute A through D. When you're talking about A through D, you're trying to account for the number of standard deviations you would need in order to get something that's corresponding to a family associated with these levels of confidence. You kind of already know what some of them are. And you can use the normal calculator on Statcrunch basically to come up with these. When you're thinking about 2A, you just might want to check, see if it's plausible, see if these conditions seem satisfied in this case. But I would like people to come up with a confidence interval on B and then maybe talk about it in C a little bit. So let me stop right there. I've talked for like an hour. That's painful, I realize. So I'd like maybe to break into groups at this point and maybe let people think, try their hand at some of it. You can use Statcrunch to come up with the interval. You can use the formula, either way. So let's maybe take 6 groups. It's about 1:45. I'd like the groups to kind of think a little bit about those problems for a few minutes, maybe from 1:45 to, let's say about 1:53, maybe 8, 9 minutes, maybe 10 minutes, something like that. And then we'll reconvene and we'll go back and treat the problems together. So now you should have an invitation to the rooms. So I'll see you in a few minutes. So how did it go? What did the groups think? Good, good. So let's take a couple of minutes just to kind of get a sort of complete description. We'll write some stuff down. You know, talk a little bit about how the numbers or where they might come from. So here are the questions. When you're taking a look at the critical values, that's the name for the number of standard deviations that we need in order to get, or that we're associating to a given level of confidence. I guess that's what I'll say. So you might remember that we kind of already know what a couple of these are. This is about 1.65 memory serves. This is 1.96. And I think this is about 2.57. Do the groups get numbers like that?
Yep.
Okay. One final calculation, the 98% confidence level. Let's go to Statcrunch. You play the same game. You simply switch this to 0.98, and you get a critical value of 2.33. Yeah, it seems about right. So let's write that down here. So in a way, you know, all other things being equal, couple points about this when you're talking about the confidence level. All other things being equal, lower confidence is associated with a lower critical number. Higher confidence with a higher one. So higher confidence, so the critical number is an increasing function of the confidence level. So the higher the confidence level, the wider the interval has to be to get that level of confidence, all other things being equal. That fact is actually kind of important to remember. So just remember a little bit about that. To look at the more extreme example, you know, a 100% confidence interval, if you think about that weird thing that might be, it would kind of have to be the entire real line in a sense, because that's the only way that you could be sure that it contained the interval. So when you're thinking about problem 2, a couple points about it. Again, you have a point estimate of 0.49 for the proportion of respondents who expected that it would be difficult to vote in this year's presidential election. I guess this is 2020, I guess it was last year. You know, when you're checking the conditions, there's usually some independence randomization condition to check, but the only thing I'll really say about that is it's very difficult to know much about that first condition unless you have access to the actual work that people did, which we don't here. But if you're dealing with a company like Pew Research, you could assume, I think it's reasonable to assume that this has basically been satisfied. Independence condition is sort of like you're thinking that the elements within the sample don't really have any real relationship with each other. Randomization condition is that somehow you know that either you're dealing with a random sample of some kind, or if you're dealing with an experiment that, you know, participants have been randomly assigned to different groups, different treatment groups. Most responsible researchers are going to do this, or at least they're going to have an explanation about why this was not done and maybe account for it in the work. When you're dealing with condition 2, just check that the sample size n is substantially lower than the population size. And I think the condition the author gives is less than 10% of the population size. Now, of course, if you're dealing with all people who might potentially vote in a presidential election, 11,001 is not that big as a percentage of the number of voters. Forget exactly how many people voted in that election, but it was into the millions. So you're not really worried about that. If the sample is big relative to the population, it turns out that's not such a curse. The intervals that you're trying to come up with tend to be a bit narrower, and the margin of error decreases in cases like that. But it just turns out the methods that we're talking about here, when you're talking about medium data, so to speak, or small data even in this case, don't work that great. The last condition is this one right here. Just make sure that the sample size and P are reasonable. So, you know, P and N are related in a way that looks like this. So they're reasonably big. P hat's sort of near the middle. It's not on either extreme. It's not close to 1 or close to 0. Same is true for the probability of failure. Their relationship to N is reasonable. So that's the so-called success failure condition. But you can immediately see that that's satisfied because 0.49 times 11,000 is quite a bit bigger than 10. So when you've done that, I guess the question is how do you come up with the actual confidence interval, I can think of a couple of ways of doing that. One way is just by formula. 95% level of confidence is associated to a critical value of 1.96. And so the formula for our interval ought to be, in general, P hat, which is the point estimate, minus 1.96 multiplied by the estimate that we have for the standard deviation. I guess I'll call that SE P hat, follow the notation of the author. And I'm just giving you just sort of a blow-by-blow description of how you might do this by hand. So you have that. So to come up with the formula, just notice that P hat is 0.49, and the standard error in this case, the estimate of the standard deviation, would be the square root of P hat times 1 minus P hat. So that's 0.51. I do need to divide by the sample size. Sample size in this case is 11,001. So the standard error is pretty small. So what I would think in this case is that you're going to find the confidence interval isn't that wide. And so, by formula, you take that, plug it in for P hat, take whatever this is, plug it in for that, you have the interval. Another way to proceed is to go to Statcrunch and go to proportion stats, one sample with summary. The number of observations in this case is, I believe, 11,001. How do you get the number of successes? Maybe I won't do this totally, but in order to get the number of successes, basically multiply 0.49 times 11,001, put that number right there. The confidence level, we don't want the hypothesis test, but the confidence level you want is 0.95, and that's another way to come up with it. Does anyone have any questions about this so far? Is this all okay to you? A couple different ways. You get 95% confidence interval using these methods. So when you're talking about using Statcrunch or using formulas, I honestly don't have much of a preference about what you use. Statcrunch should generate some pretty usable answers if you're trying to do the homework. And because the software system is sort of integrated into Statcrunch anyway. Whenever you're doing the work with the intervals, if you're sort of insisting on using the formula, my advice in cases like this is just if you're comfortable with Excel, type everything in and use cell references to come up with the formula, to come up with the numbers, basically because Excel doesn't round off. You don't really have to make as many of those decisions until the end. So let's see. There's probably one more thing to say here. If you're talking about interpreting in the context of the problem, what most people are going to say is something like, well, we have some interval of numbers, and you're 95% confident that the true proportion of people, the true proportion of voters that believe that they expect that it will be difficult to vote in the 2020 presidential election falls within that interval. But what does it mean that that's true? It just means we have one random interval that comes from one realization of the sample proportion. There are many other random intervals that you could have possibly selected in instead, but you feel comfortable presenting it as an estimate. In this case, since the sample size is so large, my sense is, since 0.49 is so close to 0.5, my sense is that the confidence interval is actually going to be quite narrow, so you get kind of a precise estimate. About half, you feel like about half the people, it's usually a number that's in there somewhere, but you present a range of numbers. Is this okay so far? So the last thing that I would like the groups to do is this question 3. I don't really want to focus on the conditions. You can verify those pretty quickly. I'd like the groups to very quickly think about the problem and then come up with the 99% confidence interval. You can interpret it, that's the normal interpretation, but instead of writing down that extra step, I'd like people to think about D. So there are two things really on problem 3 that I want the groups to consider in the final few minutes. That's part B, what does the 99% confidence interval look like? And then maybe come up with an answer to part D of that question. So let's break up into groups, about 2 or 3, maybe take about 4 or 5 minutes, probably meet together with a couple of minutes to go. I'm going to focus a little bit on D. I'm hoping the groups will come up with the interval so I won't have to do it. So I'll just write it down and then we'll talk a little more about D. So now you should have the invitation to the room. So we'll meet again in a few minutes. All right, so let's try to, I think people are coming back into the main room. So the rooms will close in a minute anyway. So I'd like to try to finish up the discussion about this question about the confidence interval. So let me share the screen. I'm hoping the groups kind of were able to come up with the interval, but the question that I would like to consider, I think this may be the last one. So we were thinking about both B and D, the 99% confidence interval in this case, and then the question about the interpretation kind of context. Should they conclude that the percentage of females in the labor force is lower than the EU's rate of 46%? So let me very quickly compute the confidence interval. You can use Statcrunch to do this almost instantaneously. Basically, you have 229 successes out of 525 observations. And so you can use that very quickly to come up with the confidence interval. So you go to stat, proportion stat, one sample with summary. Number of successes is 229. I can't remember that, 525, I think. I want to compute a 99% confidence interval. So I enter that, and I get a summary that looks a bit like this. So I get a sample proportion of about 43%, which is lower than 46%. So maybe the answer to D is that the Department of Labor should think that we're lower. But my answer to that last question was that maybe it shouldn't, because if you look at the lower and upper confidence limits that you're talking about, the lower limit is 0.38 and the upper limit is 0.49. So, to write this down, what I'd say is that the 99% confidence interval ought to look a bit like that. And I think, I'm not sure how the groups felt about this, about the question in part D, but, since 0.46 is within that interval, it's one, and the interval can be even greater than 0.46. I think what I would say in this problem is that there's no real evidence from the information we have here that the percentage of females in the labor force is lower than the EU's rate. There's no evidence of that in this case, if that makes sense. So, and that's because 0.46 is in the interval. So probably I'll write that down next time. But, before I write anything down, does this make sense to you? The confidence interval that we have actually contains 0.46. So that doesn't provide evidence against the belief that the proportion we're talking about in the US is less than 0.46, even though the exact sample proportion is, confidence interval is kind of in there. Is this okay? Do people see what I'm trying to say with this? The confidence interval does contain the 0.46, and that kind of has some meaning. So I'll probably write that down next time. It's about 210, so I think probably that's enough for one day. Again, make sure you're continuing to work. So I'm gonna stop the recording.